Hello, this is Dr. Stutzman, and today we're going to talk about the integral test for series convergence. So we're going to use an integral that's very closely connected to a series to see if the series converges or diverges. So if compare the area of the integral, and this is going to be a improper integral. Compare it with the area of the series. So let's look at 1 over x squared and 1 over n squared. This is the infinite series because we're going to count up an infinite number of terms, and this is an improper integral because one of the limits of integration is infinite. So this is the function 1 over x squared. Well, the series 1 over n squared is going to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared forever. We're adding an infinite number of terms, but is that infinite sum going to be convergent or not? Is it going to approach infinity or not? So here is 1 over 1. That's the area of that first box. The second box is 1 over 4. And then 1 over 9. And 1 over 16, and so forth, going forever. They're kind of working lockstep with each other. And we're going to find out that if the area under this curve is finite, then the area of the series is also going to be finite, because we can also think of that sum as not being in front, but we can make it behind, and it's only going to be off by the area of one of that first box. That's 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. We just kind of put it underneath instead. So let's find out what is this infinite area, the area under this curve. And we're going to find that out by doing a limit as b goes to infinity of the integral of 1 to b of 1 over x squared, or x to the negative 2 dx. Use the power rule to take the antiderivative. The limit as b goes to infinity of antiderivative of x to the negative 2 will be x to the negative 1 divided by negative 1 from 1 to b, which is the limit as b goes to infinity of negative 1 over b minus a negative 1 over 1. Well, 1 over b as b goes to infinity goes to 0. So I get 0 minus a negative 1, or 1, which means that this integral is convergent. So the area, this red area, is an area of 1. Well, the series is definitely not going to be the same as 1, but it's going to be also going to be convergent because it's bigger than 1, and that series is going to be convergent also. So let's do another one. Let's do 1 over x compared to 1 over n. Well, the graph almost looks the same. It's a decreasing function, but it's a little bit different because instead of being the squares, this is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Or 1 plus a half plus a third. Instead of being 1 plus a quarter plus a ninth plus a 16th, it's a little bit different. Let's find the area under this curve. and see if that's convergent or not, which would tell us about the area of the series, of the sum of the series. So if I want to find the sum of that series, I'll find the area under the curve from the integral, which is the limit as b goes to infinity, the integral from 1 to b of 1 over x dx. The antiderivative of 1 over x is the natural log of x. Well, it's the natural log of the absolute value of x, but since x is always going to be a positive number as x goes from 1 to infinity, that's okay. Limit as b goes to infinity, the natural log of b minus the natural log of 1. Natural log of 1 is 0. Natural log of b as b goes to infinity is divergent. It goes to infinity. It goes very slowly, but it does go to infinity. So that's infinite, which means that the integral is divergent. And the sum, the infinite sum, which in this case was a little bit bigger than that, is also divergent. One over n is a very important series called the harmonic series, which we'll talk about a lot in this unit. All right, so in general, the integral test compares two very similar functions. One is the series, and one gives me the integral. And they work in lockstep with each other. If one converges, the other converges. If one diverges, then the other diverges. In order for this to work, the function has to be positive, has to be continuous. Continuous, you can check to see if it's a nice function like a polynomial or a rational function with no zeros in the denominator. Those are things that make things not continuous. Decreasing, you can check to see by calculus if f prime of x is less than 0, because that tells you if a function is decreasing. If you find out that this integral converges, if you find that it has a limit, whatever that limit is, let's say the limit is L, this sum is not going to be the same. They might both converge, but whatever this integral converges to, the series will probably converge to something a little bit different because there's a little bit of a difference in the area from those two curves. All right, let's do an example. Determine if the sum from n equals 2 to infinity of 1 over n log n converges or diverges using the integral test. We start at n equals 2 because when n equals 1, I'm dividing by natural log of 1, which is 0. So we're going to start a little bit later, start at natural log of 2. So my function f of x is 1 over x natural log of x. And in order to do the integral test, we have to check to see if it's positive. Well, it is positive because x is positive and natural log of x is positive. So that fraction is also going to be positive. Is it continuous? It is continuous because both x and natural log of x are continuous, and none of them are going to be 0 as long as x is greater than 1. It'll be continuous. Is it decreasing? Well, it's decreasing if f prime of x is less than 0. And I'm going to check that by taking the derivative. This is f of x is I'm going to rewrite that using a negative exponent. So f prime of x using the power rule will be -1 times x natural log of x to -2 power times the derivative of the inside, which is going to be from the power rule first times the derivative of the second plus the second times the derivative of the first, which is 1. And since x and natural log of x are both positive, that product is positive. And since x times 1 over x is positive and natural log of x is positive, the sum is positive. And -1 is a negative number. So negative times positive is negative. So f prime is decreasing. So now I can use the integral test. The integral test says, let's find out if the integral from 1 to infinity of 1 over x natural log of x, the same function, is that convergent or not? Well, this integral, the way I'm going to have to do this integral will be u substitution. If he'll let u equal natural log of x, then du is 1 over x dx. That's nice because I have 1 over x dx right here. And I have natural log of x here. So now I have the limit as b goes to infinity of the integral as x goes from 1 to b of 1 over u du, which is the limit as b goes to infinity of the integral from x equals 1 to b of, I forgot to take the antiderivative. The natural log of u from x equals 2 to b. And u is natural log of x. So get the limit as b goes to infinity, the natural log of x all right, as b goes to infinity, this is a constant. But natural log of b goes to infinity. It goes incredibly slowly, but does go to infinity. So this is a divergent integral, divergent improper integral. So because the related integral is divergent, then the original series is also divergent. All right, to try it for yourself, let's determine if this series is convergent or divergent using the integral test. Use a very similar function, f of x is 1 over x to the 5th. Check your conditions for using the integral test, whether or not it is positive, whether or not it's continuous, and whether or not it is decreasing. Once that's all done, then check the associated improper integral. And if that's convergent or divergent, that'll tell if the original series is convergent or divergent. And you should find out that it is that it does converge. All right. Ask your teacher if you have any more questions, and we will see you on the next video.